So we have velocity time series wherein you have this velocity in y-axis and time in x-axis. The velocity varies randomly with respect to time. This is taken at a particular point in space, but with respect to time we have a high number of data points. So this is plotted in this way, and this will tell you that the velocity is randomly fluctuating. I do not get meaning out of this directly, so you need to do statistical processing, and that statistical processing can be done, and you can get some information out of it, and those information will be like I can take a mean of the entire data set, and I can find that this is the mean velocity. I can name it u bar, and then above and below the mean you might find the fluctuating components. This will be a positive u dash, and this will be a negative u dash. So this will be a positive fluctuation, and this will be a negative fluctuation, and so on. So you can see this information from this graph. Like if I choose a particular point in space, for example, I have a room of turbulence, and I choose an arbitrary point, and I start recording velocity data. I will be getting a random time series graph, and I can process that, and I can infer what that says. So if I choose a particular point in this graph, for example, I choose this particular point. So if I want to infer any information from this, I can say like this is the fluctuating component u dash, and this is the mean component u capital dash. So at this particular point, u tilde is equal to u bar plus u dash. So it will tell you that at a particular instant, or the instantaneous velocity, you can find two components in that. One will be the mean component, and another one will be the fluctuating component. This we have already discussed, so we know well that the instantaneous velocity can be decomposed into two, that is mean component and fluctuating component, and this is called Reynolds decomposition. So here we have this instantaneous velocity u tilde, which is equal to u bar plus u dash, the mean component plus fluctuating component. Now if you average this components individually, like mean component and the u dash components, that is the time averaging, you will get u bar. This is the average of u bar. It will give you u bar again. U dash, if you find average of this, it will be 0. Why this happens is, suppose if you find the first one, this is average of this particular component, this is mean component, it is already the average value, and if you take again average, it will be the average only. But fluctuating component, if you see, this will be over and above the mean. It can be positive fluctuation and it can be negative fluctuation. If you average it for a long time, the positive and the negative fluctuations will balance out each other, and the average will go to 0. That's where you will arrive at this solution. So this Reynolds averaging and Reynolds decomposition, you have to use this in your conservation equations to arrive at Reynolds averaged continuity and momentum equation. So first we will start with the continuity equation. We have dou ui by dou xi equals 0. So we consider this to be instantaneous. So you know that instantaneous velocity will be decomposed into u bar plus u dash. So if I substitute this in the equation, we get dou u bar plus u dash by dou xi equals 0. We can expand this and write it as dou u bar by dou xi plus dou u I dash by dou xi equals 0. We know that from the previous slide, this goes to 0. Hence our equation will be like a dou u I bar by dou xi equals 0. This will be the Reynolds averaged continuity equation. Now once we know this Reynolds averaged continuity equation, we need to derive Reynolds average momentum equation. So we need to consider a momentum equation first, that is an instantaneous momentum equation. So dou u I, that is tilde by dou t plus uj tilde dou ui tilde by dou xj equals minus 1 by rho dou p by dou xi plus nu dou square ui this tilde by dou xj dou xj. So you need to find whether the equation is consistent or not. So the equation is written in I, so jj cancel out, so I stands here, so this will be I, this jj cancel out I, so equation is written in I, so it is fine. So we can start with substitution of each and individual components, that is the decomposed components in each and every term, such that we will get dou ui bar plus ui dash. So this will be the first term by dou t plus uj bar plus uj dash times dou ui bar plus ui dash by dou xj equals minus 1 by rho dou by dou xj of p bar plus p dash plus nu of dou square by dou xj of ui bar plus ui dash. So this will be the substitution. Once you get this, you need to split this into terms and average it. So this will be dou ui bar by dou t plus uj dou ui by dou xj plus uj dash dou ui dash by dou xj equals minus 1 by rho dou p dash by dou xi plus nu dou square ui by dou xj. So this is the equation you arrive at. Once you arrive at this equation, you can take the left hand side last term to right side and then rewrite the equation. It becomes dou ui by dou t plus uj dou ui by dou xj equals minus 1 by rho dou p bar by dou xi plus nu dou square ui bar by dou xj minus dou ui uj. This is about the third term in the previous equation on the left side. So you get this equation. In this equation on the right hand side you have all the terms with dou by dou xj. So what we can do is we can bring dou by dou xj out and remaining terms can be into bracket, such that dou ui by dou t equals plus uj dou ui by dou xj equals dou by dou xj minus p bar by rho delta ij. This is the Kronecker delta, wherein the output will be dou p by dou xi. So this j and j will cancel and you will get in terms of I. So then you have the viscous term that can be rewritten as 2 nu Sij. Then you have the last term ui dash uj dash. Now you can easily infer meaning from this. This will be the temporal term, this will be the advective term, this will be the pressure term, this will be the viscous stresses, this will be the Reynolds stresses. Now while deriving continuity equation, we substituted the Reynolds decomposition and averaged it. We got a Reynolds average continuity equation which was similar to the original continuity equation. But while deriving Reynolds average and momentum equation, the equation is almost similar but with one extra term. This is this. So you have the equation with a new unknown which we name it as Reynolds stress, and we need to see how we are going to solve this. So this is the equation, we called it Reynolds average Navier-Stokes equation or Reynolds average momentum equation or Reynolds mean momentum equation. So there are different names by which you can call this equation. So this is the equation, we will be using it for studying turbulent flows.